In field theory, there are those dreary calculation days. Today's one of them. I think we've only had one other dreary calculation day so far. But not to fear, because Johnson will be covering one of the calculations next week, very slowly. So don't be alarmed if you're missing some of the steps, or even a lot of the steps, because I tend to skip a lot of steps, as you've realized already, because if I went through each step, we never get through anything. They're just too long. Okay, so what are we doing? Where are we going? Okay, where have we been? So we have started discussing QED, which is one of the, probably I would argue, and I think a lot of people would argue, it's like the crown jewel of quantum field theory that sort of sets the stage for everything else. That once this formalism was established, it really sort of sent quantum field theory on a rocket ship. However, there was a big roadblock. There was a big hurdle in the way of quantum field theory that, in fact, in the historical development of the subject, made people almost throw it out, had people stuck for a decade. And that was this question of divergences, which the last few lectures from Johnson have really taken you a bit more in depth with these divergences, UV divergences, right? And how do we regularize these divergences, right? So we are basically going to spend the rest of the class, other than the last 3 weeks or so, where we talk about Yang-Mills theory, on renormalization. How do you get rid of divergences? That's basically what the whole rest of the class is going to be on. And it turns out that it not only is it a necessary algorithm for solving problems in QFT, it actually gives you a lot of insight into new physics, which is always nice. So today I'm not going to jump right into corrections or radiative corrections. We're going to start with one more scattering. I'm going to go through the calculation for Compton scattering. And after we're done with Compton scattering, we're going to start talking about radiative corrections. As you know, all of the things we've been looking at up till today have been tree level. Everything has been tree level calculations. And we're going to start introducing our notion of radiative corrections, i.e. in Feynman diagrammatic language, that means adding loops. Okay, that's what it comes down to. So I'm going to go slow, and we're going to start with soft radiation, or Bremsstrahlung. That's the German word for it that people use. So what is the homework? Other than our meeting tomorrow, the homework, I'm giving you quite a bit of reading. So it's Lancaster Blundell, 31, 32, 31, 32, 33, 41. This will take you some of the basic ideas of renormalization in QED, namely mass renormalization, which is the simplest way to think about this kind of thing. If you recall, I said very early on that there's a difference, that the coupling constant we've been using, alpha, g, lambda, that's not that mass associated with that coupling is not the real mass. Okay, it's not the real coupling. We have this idea of a running coupling or virtual mass. So that's where this idea comes in, and you'll see the specifics of that. Then I want you to read chapter 13 of Weinberg, which talks about infrared divergences and soft theorems. So now you'll have the machinery to understand the soft theorems. And I really want you to read this. This is very important because you've gotten the flavor that soft theorems play a very important role in some of the research going on. And now you'll have enough of the QED machinery to understand what's going on with the soft theorems. So I would read that. And then there's 2 papers I want you to read. Now we should start actually reading papers. The first one is, I don't even remember the dates. Hold on. I think I have them written down. Yes, the first one is Weinberg, If you can't find them, let me know. I'll send them to you, but you should be able to. 1965 physical review, because it's hard to find otherwise. And it's infrared photons and gravitons. And gravitons. And the second paper I want you to look at is by Schwinger, Julian Schwinger. This one is more important right now. You should look at this one. From 1948. Physical review on QED and the magnetic moment of the electron. So this was a huge triumph that Schwinger calculated the magnetic moment of the electron. For those of you that have watched Tony Z's pop lecture, he mentions this because it is one of the biggest achievements in physics, this calculation Schwinger does. It's a shame more people don't know about this because this is probably the most famous paper of the 20th century. It is probably the single most famous paper. It's been the most cited, it's been the most used. And in fact, Feynman did not calculate the magnetic moment until 1950. So it took him 2 years to get the same result Schwinger got. Schwinger got it first using the techniques of generating functionals and so on. I'm not gonna, we'll do it exactly how Schwinger did it. I'm just gonna follow his argument. So this is definitely, every student of field theory should read this paper. And you might not understand all of it because Schwinger is very eccentric. He does things in a very weird way, in his own way. Everything he wrote was in his own way, literally everything. And also you should read these if you have time. He has a series of papers called The Theory of Quantized Fields. I love these papers. They're wonderful. And they're just like a overview of what quantum field theory is. And they're written from 1951 up. There's like a series of 4 or 5 of them. I have copies of all of these if you can't find them, but I love these papers. Theory of quantized fields. I actually read all of them right after I took quantum field theory for the first time, and I really thought they gave me more insight. Okay. And this paper by Weinberg is a very famous paper too. And it's basically everything in chapter 13 of this textbook, just recast in more formal language. So, okay, any questions from last week or in general before we get started? Okay, let's get started then. So what is Compton scattering? Compton scattering, you probably heard of Compton scattering, right? In high school? Or Compton, what do they talk about with Compton in high school? Compton wavelength, probably? Something like that. I remember hearing the name Compton in high school. I don't remember in what context though. But basically, what's the process of Compton scattering? So let's write down the process and then do the calculation. Get ready. My chalk is ready. Let me just think about it. So Compton scattering is a very simple process, actually. It's E minus gamma to E minus gamma. So you basically just have an electron propagating through space-time with a photon crashing off it or emitting from it. And as it moves through, you have another photon emitting from it. That's all. That's really all Compton scattering is. And there are 2 tree level diagrams we're going to have to think about. So this is my electron just moving through space with momentum p. Here it's p plus k because I'm going to draw the photon. Here it's p prime. So it emits the photon and then it does its funny business. So here is the photon crashing into the electron with momentum k. Okay, and here is that momentum going out with momentum k prime. Okay, so the photon comes in, collides with the electron, you get a vertex, and then they move on their merry ways. Okay, similarly, the second tree level diagram looks like this. That doesn't look any different, but you have P, you have P prime, and the photon could come from here. Momentum K. K prime, and then hit it from here. Momentum K. Okay. So those are our two tree level diagrams for Compton scattering. And now we should write down the cross section. Let's do that. So take a minute and think about what the cross section should be. Of course, we're going to have polarization vectors. Now we have photons to think about. Remember, where do we get polarization vectors? We get polarization vectors for external photons only, right? Internal photons don't get a polarization vector, they get a propagator, right? And the propagator has no polarization, it just has the metric. So that's something to think about, that only external. So that's why these guys are going to get polarization vectors, because what determines the photon? The gauge field, right? A mu. That determines the photon. That's the mode expansion of the photon. So how should we write this? Well, I'm going to start with U bar of P prime, the spinner for the outgoing electron. And then I have a vertex factor minus E gamma mu. I drew this kind of bad. There should be a vertex there. You know what I mean? There should be a vertex here and here and here and here. Is that clear? Those are vertices. Okay. Then I should get a polarization vector, epsilon mu star k prime, because it's outgoing, so it's star. It's the Hermitian conjugate. And then I get the propagator, I p slash plus k slash plus m over p plus k squared minus m squared. That's your standard photon propagator. And then we get it for the other. Then I get U bar of P prime, but now I have to get it for, I got it for this, so now I have to write it down for this photon. In either. And then I get another vertex factor minus I E gamma mu, right? And let me see. Oh, wait a second. Let me think about this. Oh, yeah, I made a mistake because I want to calculate both processes so I don't get another U bar, right? Now I have to get this guy. This is ingoing, right? So it's different. So I get the propagator. Okay, yeah. Then I get minus I E gamma mu. This is just for this first diagram. Sorry, my apologies. Yes, epsilon mu of k, U of P. Okay, sorry. Does this make sense for the first diagram? U of P corresponds to this. It's ingoing. This is also, this is outgoing. So it's U bar. They're both particles, not anti. The outgoing photon gets epsilon mu star. The ingoing photon gets epsilon mu, okay, of k and k prime. Okay. And then we add the second diagram. So U bar of P prime, now it's easy. Minus I E gamma mu. Actually, this should be mu. I would say this should be mu. This is a whole separate diagram. Epsilon mu k. I'm going one little piece at a time, very slow. by P slash minus K prime slash minus M over P plus K prime squared plus M. That's my problem. Now I'm doing the second diagram. Sorry, plus M. Minus IE gamma mu, epsilon star mu of, what's the outgoing? K prime. U of P. That's my amplitude. Hopefully this is a simple thing. The only difference is I'm taking two diagrams down, both diagrams at tree level. Is this okay with everyone? Okay, you just plug in the rules. I think Lancaster and Blundell do it this way. They just plug in the Feynman rules. But as you guys know, intuitively, this is like trivial. The hard part is getting it into a usable form. That's the whole name of the game. This is like a middle schooler could do this, right? If I just told them what to write. This is just intuitive. So let's now do the QED process or the algorithm, right? Namely, trying to get this amplitude written out as traces of Feynman of gamma matrices. So that's the whole idea. But of course, this is not useful, but we need it. We need this expression to start with. Notice how the form of the propagator totally becomes the fermion propagator when I have external photons. We've never dealt with external photons yet. So of course the amplitude is going to look different. I've only had internal photons. So I'm just going to do some manipulation. So I always like to pull out these factors, minus IE squared, epsilon mu star of K prime. This is I mu, I m. I always call it mu. I don't know why. Should call it m. It's not mu. Epsilon mu of k, bar of P prime. I'm just pulling out all of my spinner stuff. Okay, of course now I can just, contract the gamma matrices. So let's just do that in the propagators. Now I have gamma mu P slash plus K slash plus M. Sorry, I'm going to write this down below so I can write down the whole expression. So now I have gamma mu P slash plus K slash plus M gamma mu over what? Over just my standard A plus K squared plus M squared. That's my just standard, minus M squared. I hope you're starting to notice a trend. I literally almost always make sign errors because it's just what physicists do. They make sign errors. That's life. Okay, and then I need the second propagator. The second propagator is literally just gamma mu P plus K prime plus M slash gamma mu over P plus K prime squared minus M squared. Okay, that's just basically, I'm just doing some algebra. Oh, I forgot one spinner, U of P, sorry. There, I didn't have it. I don't know, I should have just wrote it up there. Doesn't matter. Okay, we're on shell, so obviously P squared equals M squared. And for the photon, K squared equals 0 because it's massless, right? So if you work out those relationships, you can write down the following identities. That P plus K squared equals what? That P plus K squared minus M squared equals 2P dot K. I'm just using the fact that we're on shell. So this is the on shell requirement. Notice how we say virtual particles or internal particles are what? Are virtual particles on the mass shell? What do you guys think based on our calculations? Are virtual particles on the mass shell? No, they better not be on the mass shell. That's why they never have these properties assigned to them. They're not on the mass shell. So you can't use this property. Okay. Similarly, p plus k prime squared minus m squared equals minus 2p dot k prime. Let's just should work out the algebra. Remember, these are really 4 vectors, so really p is really p mu, right? Okay, and k is really k mu. So just that's why I can write it out like this. Okay, and then we can also write p slash plus m gamma mu. So this quantity, actually, let me write it with the spinner out here. U of p will make the calculation simpler in the following way. We can write it as 2p mu. I'm just doing the multiplication here. Minus gamma mu p slash plus gamma mu m with p. Just multiplying this guy. And I'm just going to finish manipulating this up here. And this equals two p mu u of p minus gamma mu p slash minus m u of p. And this equals 2 p nu u of p. Okay. Okay. There's a lot of algebra here, so go through it slowly. Okay, can I erase? I have a new rule. You want to know something? I heard something really good. I was in a lecture, and the professor had a rule. I was just sitting in because the professor was covering a topic I wanted to learn. So I just sat in. I asked him if I could sit in, and virtually, obviously. And he had a rule, and I like this rule, so I'm going to use it. He said, if you ever need a minute of silence, just ask, right? Like if I'm going too fast and you need a minute of silence, just raise your hand and ask. It was the best rule ever because sometimes it gets a little overwhelming and someone would raise their hand and say, can I have a minute of silence? And it really helped because you can just like process what's being said. So we have that rule implemented here. If you ever need a minute, just say, Kyle, I need a minute and I'll stop, okay? Otherwise, I like to go kind of fast, so. I'm not that fast though. I'm decently fast. I was watching this mathematician give a lecture and she said, when you're young, you don't need to lecture with notes. And so you go very fast. And as you get older, you find that you need notes when you lecture. So you become slower and slower. So eventually it will happen to me. Not yet though. I still have my facility. Okay, so let's rewrite the amplitude. Okay, let's just think about what we have so far. Okay, I have minus IE squared, epsilon u star k prime, u of k prime, epsilon u of k. gamma mu p slash gamma nu plus gamma mu. I'm just trying to remember what we just wrote down. This should be k slash, I think. I'm just trying to remember what we wrote down. Yes, 2p dot k, 2 gamma mu p. That was from the last expression. I'm just using that. Plus minus gamma nu k prime slash gamma mu over minus 2 p dot k prime. I'm just using what we just computed. I'm just now plugging that in. Plus 2 gamma nu plus 2 gamma nu p mu. Okay, if you didn't follow the algebra, do you know how I got to this step? Is that okay? I'm just plugging in what we just calculated. That's all. If you don't know how I got this and this, don't worry, work it out. Okay. Is everyone okay? Okay. We just started. So recall the identity that u bar of p prime u of p is equal to what? This should be like very familiar to you now. P slash plus m. I think Lancaster writes this guy down a lot. And also recall, I'm going to impose the following identity, that epsilon mu star, epsilon mu equals the metric. That's the following identity I impose, where this is just a sum over all polarizations. Why does this work? You'll see. This is a very, sorry, minus G mu nu. Yeah, you want it to be minus. This is an important identity. So look it up. Or I'll give you more physical intuition, but it's not intuitive. Definitely not. Okay, can I erase? Really, the way you should approach these is, okay, I have an expression for the amplitude. And now what can I do to simplify it? What can I work at? What are my identities? I hope you're starting to realize it's really not that bad, as long as you just know the relationships between the objects and can do a little bit of algebra. It's not absolutely insane. It's not a very hard calculation. Okay, so let's utilize those now, which I think the top expression you've seen. Okay, but before we do it, we're going to have a little aside. So just remember that top expression. You guys read about word identities, right? Okay, so let's use this idea that epsilon nu goes to minus G mu nu to talk about a word. What kind of, let me just, I won't, let me do the calculation, then I'll motivate it. So let's say we have a blob and we have all kinds of things going on in this Feynman diagram. All right, and we have one external photon. Okay, we have one external photon jutting out of it. So I can write the amplitude in this way. Im of k is defined as I, and I'm going to call this m mu of k. So this is like most of the amplitude. Okay, all the bits of the amplitude I'm putting in there. Epsilon mu star of k. Okay, that's the polarization vector for the outgoing photon. Is that okay? This is just most of the amplitude. And those of you that have read about the word identity are probably going, yeah, this is good. This is a piece of it, m mu, right? Okay. So obviously, I have to put this in the form I need to use it, which is a sum, the modulus squared of the sum over polarizations, right? Why put this in the modulus squared? Right. Epsilon mu star of k and mu of k squared, right? That's what I'm going to need to put in my cross section. And what this gives me is a very simple expression. It just gives me epsilon mu star of k, epsilon mu k prime, m mu of k, m mu star. That's just taking the, we'll just call these all k. No need to label them. Okay, that's just taking the square of this guy, right? And so now let's do the following. So now I have the squared amplitude for the very simple process, right? This is just one photon, right? Coming out. It's not even really a real process because we don't have much going on. I'd like to label my momentum k mu, photon momentum, as k0, 0, k. So it's a photon with momentum along the 3 direction. Okay. And I'd like to label my 4 vectors, so epsilon mu1 as 0, 1, 0, 0, and epsilon mu2 as 0, 0, 0, 1. So there's 2 polarizations. Oh, sorry, let's do it like this. Okay, so there's a polarization along the 1 direction or the x direction and the y direction, along the 2 direction. If I had a number here, it would make no sense, right? For a polarization vector. The same, because that's the time direction. What does that even mean? Okay, and why did I label 2 polarization vectors? Because this is m mu. This is going to be 4 different amplitudes, right? Because there's 4 different polarizations. Okay, so oftentimes I drop the mu's and the nu's and everything. They're always there, right? So like there's many different things we have to plug in. At the end of the day, these are just plug and chug kind of things. That's not really, it looks very intimidating, but when you really just break it down, so that's why I've written down 2 polarizations. So now I can write down my amplitude in the following way, in a more suggestive way, where now I take the sum over polarizations, epsilon mu star of k, m mu of k squared. And now I can write this as the sum of 2 amplitudes, m1k squared, 2k squared, where the different polarizations match with m1. So maybe m1 is the polarization in the 1 direction, and m2 is the polarization in the 2 direction. I don't know, whatever you want. Okay, so let's pause and let's recall how are external photons created, okay, in QED. Well, there's an interaction term that goes d4x e j mu a mu, right? Where you have the gauge field, you have a current, and you have a charge, and that creates a photon. Where usually in QED, we say that J mu equals psi bar gamma mu psi. Okay, and that's what we call the vector current or the Dirac vector current. So we expect, so is this okay? Have we seen this kind of expression? I hope so. Okay. This is why it's so important to do your homework reading. Okay, so we expect that the matrix element for m mu should have to do with this. So in other words, how can I write this? We expect that m mu of k is going to be a matrix element, obviously, that's what that is, that takes the following form. D for x, e to the I, k dot x. Okay, and then I'm going to have a matrix element with some final state, j mu x I. Okay, that's what we expect. Because of course, this is the current. Okay. Okay, so where am I going with this? How am I motivating this? Well, F and I are all the particles except the photon. I'm only looking at the photon. And what is our famous equation from Noether's theorem that we must impose? Right, d mu, j mu equals 0, right? And what does this tell me? What does this tell me as a result from Noether's theorem? That something is conserved, right? And what is the conserved quantity? Can someone tell me what the conserved quantity is? What is this guy? Feel free to take a guess. I mean, what is J? J is the current, right? So it's a conserved current. So similarly, we can write down a similar identity in field theory, where now we say that K mu M mu equals 0, where K is some momentum vector. So let me put that up top. Let's talk about what that means. So it's the direct analog of current conservation for scattering amplitudes, except we want it to be for all amplitudes. So we have K mu M mu of K equals 0. And we want this for all scattering amplitudes, and we want this for all momenta in the scattering amplitudes. What do I mean by this? Momentum is constant in each scattering amplitude, right? The momentum you put in is the momentum you get out. Therefore, the divergence, K mu M mu, the divergence, taking that whole derivative, must be 0. You cannot have any change. And this is the famous Ward identity. This is a very important result. I'm not going to do the full derivation. It's very, very long. If you want that, I'm sure it's online. But this is the famous Ward identity. And it's the direct analog of current conservation in electricity. It's the direct analog of d mu, j mu equals 0, of current conservation in electromagnetism. And the best way to think about the Ward identity, and we are going to use Ward identities a lot, especially, in fact, a lot of times you're trying to find a Ward identity. That's kind of like an important piece of solving a problem, because what this is giving you relationships between scattering amplitudes. That's the best way to think about this, right? I can have 4 different amplitudes, and they must be related by this identity. Therefore, I can determine everything about K mu in each situation. Okay, so it gives me the relationship between scattering amplitudes. Therefore, if I replace epsilon mu in my amplitude by K mu, if instead of a polarization, I assign it a momentum, the amplitude vanishes, okay, for both pieces, because I get a 0 from the Ward identity, via the Ward identity. Okay, is this okay, somewhat? Okay, I would read more about it because it's so important. Okay, let's go back to our Compton scattering, because we're going to need to use this idea to simplify our expression. So let's go back to Compton scattering. And now that we have the Ward identity, That's a nice little tool. So now I'm going to send epsilon mu of k to k prime. Okay. I'm going to send that polarization to some external momentum, and I'm going to send epsilon mu star of k to k. Motivating this and thinking about this from the perspective, sorry, k prime, k mu prime, k mu k. I always get my primes mixed up, so. And that's the motivation. So recall, I have k mu, and I have labeled it as k, 0, 0, k. That means that my amplitude is going to go k m0 of k minus k m3 of k equals 0 by the word identity. That means that m0 must equal m3. Right? This is in the 0 direction for the momentum. This is in the 3 direction. Okay. I'm just simplifying what we're going to write down for Compton scattering. Can I erase this board? Okay. Okay, let's just write this out generally. This way we can have this expression. Sorry, I'm jumping around a little bit, but we need to have these tools written down. So let's just write this guy down. Let's write down a general expression for epsilon mu star, epsilon mu, m mu of k, and mu of k. So how would this square look like? And of course, this is star. This is the modulus squared. And I hope it's obvious that I can just write down this inner product like this, m1 squared, m2 squared, m3 squared, m0 squared. And I have not ignored that, don't worry, because I'm writing minus g mu nu. That comes from the identity I wrote before with polarization vectors. M mu of k mu star. These are all equivalent. Actually, wait a second. Why do I have a minus in front of g mu nu? M mu star. I would be suspicious about this. It might have worked in one calculation. I'm suspicious about this. Just letting you know. I think I might have made one sign there, but that's okay. Okay, can I erase this board? Okay, we're going to need one more piece of machinery. And that will be we're going to need one more piece of machinery. Let me think about how I want to present this. Just a second. Okay, so the final piece of machinery we're going to need. So now let's go back to Compton scattering. I had written out an expression for m squared, right? That had some terms in it. And I said, okay, let's take a break. We made a line here and we started talking about the ward identity. So now let's go back to our expression for Compton scattering. And now let's write it as some expression that goes 1/4 times the spins, which is what we've been working with. Because now I'm letting those polarization vectors go to k's. then I have m squared. But now we know something. Okay, hopefully this clears it up. If we let the epsilons go to k's, we can't just do that. That's not completely kosher, because what is the word identity saying? The word identity is saying k mu m mu equals 0. That means that we're going to really have to write this out now with 4 terms for m. And those 4 terms come from the 4 possible momentas the photon could have, the emitted photon in Compton scattering. Okay, so what that means is we're going to have a very complicated, it's going to be a very long expression, okay? So bear with me, but what you should be looking for is 4 terms. And we'll take those 4 terms and we'll write them as traces, okay? And this is what Klein and Nishina did. So Otto Klein from Klein-Gordon and Nishina, they took they did the first calculation for Compton scattering, and they took the 4 terms and they wrote them out as traces. So I'm going to write down this expression. It's long, so don't be scared. Don't be scared, I promise. It's really not that bad. It's just. So of course the metric is going to pop out because of the relationship between epsilon and g. Okay, epsilon mu star, epsilon mu, I'm using that identity here. Mu sigma dotted with the trace slash plus m. I don't think Lancaster-Blundell went into this much depth with this, or did they? Maybe they did. Maybe they did. I don't know. I'll take a look at it. Now I'm just going to get the terms I've been working with. Gamma mu k gamma mu. Gamma mu p mu 2p dot k. This is m squared, so now I'm going to get 4 of these guys, right? Just by squaring the amplitude. Plus gamma mu k prime gamma mu plus 2 gamma mu p mu. I think so. Sorry, minus 2. God dang, science, man. 2p dot k prime. That's just the expression I had on the board, right? Before we had this discussion. And now I just have to dot it with the square. So p slash plus m. Now I'm just dotting, it's squared, so I just need the thing over again, except with different indices now. So I have gamma sigma k gamma rho. I'm going to write this guy down here so it's not broken up. Gamma sigma k slash gamma rho plus 2 gamma sigma gamma p rho over 2p dot k. Plus gamma rho k prime slash gamma sigma plus 2 gamma rho p sigma over 2p dot k prime. Okay. I'm just squaring it and adding new indices. I'm not doing anything fancy. Is this okay for the amplitude? Yes? Okay, so now we have the amplitude written in this form. We're getting closer. Someone get the trumpets. We're getting there. We're getting there. But now Now comes the cuckoo part, because now each one of these terms can be written as traces, these numerators. So yeah, let's do it. It's going to be pretty long. Just a fair warning. So here's how I'm going to do this. Does everyone have this written down? Are we okay? Okay. Okay, time to write these all out, the traces. So I'm going to do it in this way to make it easier for me. And I'm going to need some help from you guys. I'm going to need you to tell me the numerators, okay? So I can compute the traces, because I'm not going to remember them. E to the fourth, and we'll call this 1. Or 2 p dot k. Oh, no, not just p dot k. Plus 2. No, this was 2 p dot k. This was 2 p dot k, right? In the denominator? Or was it 2 p dot k prime? I don't remember. I don't
Just 2 p dot k.
And then this was 2p minus 2 p dot k prime, right? Right?
Not minus.
Just plus? Okay.
Yeah.
Okay. Now I'm going to have to compute 4 traces. So can someone say the denominator of the first term, and I'll compute the trace. I know I need a trace. So can someone just tell me the denominator? Actually, I'm not even going to write down trace, because remember in the last expression, I wrote dot trace, right? I wrote trace. So I'm just going to compute the trace now. Can someone read it?
Gamma mu k slash gamma nu plus 2 gamma mu p nu.
Okay, good. Like that, right? Okay.
P nu, not k at the end.
Yes, good. Okay. You already know you're going to get a bunch of weird factors. I'm just trying to figure out how the terms are going to come together. Okay, I'm pretty sure I got it. Scratch this. Okay, that's correct. So this is 1. Okay. Okay. Looks a little daunting, but it should look familiar based on the other traces we've computed. It's not, it's kind of the same thing. I'm not going to do 2, 3, and 4. Okay. It's an exercise. I'm going to give you the final amplitude. So I have the final amplitude written down. So I'm going to give you the final amplitude because I did 1 for your entertainment, for your enjoyment. Okay, can I erase this? I'm like 99% sure that's right, but please check me. Definitely check me. That was kind of hard. Okay. Okay. Okay, very good. Okay, I'm going to write this out in Mandelstam variables, okay? And then write down the final one. Okay, so I've called S equals P plus K squared equals 2P dot K M squared equals 2P prime dot K prime plus M squared. And I've called T equals P prime minus P squared equals minus 2P dot P prime plus 2M squared equals minus 2K dot K prime. And I've called U equals K prime minus P squared equals minus 2K prime dot P plus M squared equals minus 2K dot P prime plus M squared, where the following relationship between Mandelstam variables, S plus T plus U equals 2M squared. Okay. That's why I don't use notes, folks, because then I would go that fast for everything. I once had a, see, you know, if someone's using notes, it's going to be bad because they are just zooming through it and you can't even think. Okay. Are we okay? I would highly recommend going to Lancaster and get a sheet of loose leaf and go through each step. You need to do that. Until you do that, you're not going to feel comfortable. And moreover, you know how to get good at physics or math. You have to do problems. This is, I like to think my lectures give you a skeleton. That's what my lectures do. And they give you the concepts. But I'm not teaching you how to calculate here. You'll teach yourself how to calculate. That's important as a physicist. You need to be able to compute things. That's the only way you understand. I never understand anything until I do a calculation. Then you say, okay, now I'm starting to get what's going on here. Okay, can I erase this? Okay, so I can write down the amplitude in terms of Mandelstam variables now, which I'll do. Okay. Even something like Mandelstam variables, you have to do the calculation. You have to convert them, and otherwise it's not gonna, it's just a bunch of letters. Wow, okay. Okay, you work this whole thing out, you work out the traces, and you get this in. 1/4 M squared, sorry, sum over the spins. All the Mandelstam variables, get out of there. And you get 2e to the 4th P dot K prime over P dot K P dot K over P dot K prime plus 2m squared 1 over P dot K minus 1 over P dot K prime plus m to the fourth 1 over P dot K minus 1 over P dot K prime squared. Okay. Of course, this means absolutely nothing until we put it into a cross section. So we have a whole 10 more steps to do. So let's do that. Let's come up with a cross section.
Is the square outside of the first parenthesis? The first close parenthesis at the end?
Wait a second, let me check. No, it should be inside here. Squaring this term only.
Okay.
That good? Okay, I'm not going to go through the whole insanity of the cross section. There's many things to read. I'm just going to write it on the board. Of course, it's not trivial. You have to pick a frame, right? You have to pick a frame of reference to scatter from and all of that good stuff. But in the center of mass frame, you get that d sigma e omega equals pi alpha squared over m squared 1 plus cosine theta. And this is the famous Thompson cross section. Sorry, cosine squared. And as you all know, Thompson crashed electrons off each other. Okay, hence the term Compton. What am I even saying? Is this Thompson or Compton? Compton. Yes. The reason, see, this is a historical misnomer. The reason this cross section is called the Thompson cross section, it's because Thompson was the first, I guess, to crash electrons off each other. It's like, I don't know. I should look into the history of that. Okay, so I trust you can go into a textbook and go through the process if you are so inclined. Okay, is everyone doing okay? Okay, that concludes this. I've obviously skipped a lot, but do some reading. Okay. It's time to finally get rid of tree level. Cut down the tree, enough. Now we go to real life, because in real life, tree level processes are only first order. And of course, they play an important role in your perturbation series, but you can't really do anything without radiative corrections. So what are the kinds of radiative corrections? Well, today we're going to talk about Bremsstrahlung, B-R-E-M-S-S-T-R-A-H, which is German for, I think, radiation or something like that. What Bremsstrahlung is the emission of final state photons in a reaction. So low energy photons that are emitted in some kind of reaction. But before we talk about, because the reason we're going to talk about this is the easiest radiative correction to talk about. Loops are harder. So loops will be next week. But today we're just going to talk about Bremsstrahlung. So what are some examples of radiative corrections in terms of Feynman diagrams? So let's say I have two, electrons, and I have a photon exchange between them here, and then perhaps there is some loop correction here. Self-emission. Okay, or maybe I have the self-emission somewhere else. Or maybe I have it corrected to a vertex. So this is at one vertex. Or here, sorry. Or maybe I have something like this. This is the most complicated guy to calculate. Where I have somehow the electron appears, then it rejiggers, and then emits the photon again. This happens too in the lab. So these would be called external leg corrections. This is called vacuum polarization. In fact, this is crucial to the magnetic moment of the electron. This would be called like a vertex correction. As you all know, these guys pose all kinds of trouble in your integrals, right? I hope you have gotten a feel for that more intuitively now. Your integrals just don't work in all of these scenarios. Moreover, they really don't work in the UV segment. That's what we're talking about is UV energy. So these are called UV divergences. And of course, they're UV divergent as k goes to infinity. Okay, that's the divergence. So there are also infrared divergences as k goes to 0. And that's what we're going to talk about today. And first we're going to handle the infrared divergences. So these are IR as you get to low energy photons. These are UV as you get to very high energy photons. So there's a sense in which you cannot incorporate the whole energy spectrum into any quantum field theory. Not possible. You first of all, you're working perturbatively. That automatically makes it an approximation, albeit a very good one. And second of all, you cannot incorporate arbitrary energy. Okay, there's some, you must cut off, you must regularize the integral, you have to do something. So let's take a break and then we'll talk about IR divergences and Bremsstrahlung. So let's start at 10:45. And I'm probably not going to be able to finish the calculation, but we'll get started on it. I look forward to learning about quantum mechanics again. I need a refresher, honestly.
So did I. I was like, oh my gosh, I remember nothing about this, but so it was good that I got it, I think.
Good. It's very important. Tomorrow for our GR class, we'll start curved spacetime. Oh no, I've been saying that for a while. We will, sorry, there's a lot of dust usually, so. No, we will start, we will continue curved spacetime. There's just so much jargon, with that stuff that you have to be careful. There's a lot of mathematical if any of you have looked into something called abstract algebra, I don't know if any of you have, the theory of groups and the actual mathematical theory, it's very jargony. Isomorphisms, homomorphisms, it's very jargon language, but basically in physics, we use that language. In fact, you'll start to see that a lot of these groups are, if you know the language, are isomorphic to one another. Isomorphic just means they're basically the same thing with different labels. You'll see that actually a lot of these, so for example, the Lorentz group is isomorphic to the 2D conformal group, which is the group we'll use a lot in our research. Okay, I'll be right back. I just want to wash my hands. They're very dusty. Okay, shall we continue? Okay. And you know, we gave Olha the fun topic for tomorrow, so it is what it is. What can I say? She got the fun topic. Not next time. Next time I'll give you a boring topic like geodesics. Ugh. Just kidding. Just kidding. No, but tomorrow I think I'm going to derive the Riemann tensor. That's what I'm going to do. But hey, my derivation of the Christoffel symbols wasn't terrible. Come on. Wasn't terrible. Come on. It wasn't that bad. We got the answer and it was okay. I finagled it, but we got it. I will try to derive the Riemann tensor tonight for tomorrow. Let's see if I can do it. I got the Christoffel symbols, so. Okay, so the IR divergences in field theory are canceled out by these Bremsstrahlung. This is a huge diagram, so I gotta draw it smaller. By these Bremsstrahlung diagrams. So let's now talk about Bremsstrahlung. Where you have some emitted photon. Okay. So we're going to spend the rest of the class looking at classical Bremsstrahlung. Classical. Okay, and then next week we'll talk about quantum, and we will talk about the anomalous magnetic moment of the electron. We'll do so that calculation will take us 2 days probably. It's a very long calculation, but let me just, yes. And we'll look at the electron vertex selection. Anyway, so let's do this classically. So classically, let's say we have something that looks like this. And let's just say I have a momentum with momentum, momentum with momentum. You know it's getting late. And as you know, I'm a little flustered. Let's say you have a particle with momentum p, gets some kick by something and moves out at momentum p prime. Okay, so kick at t equals 0 at position x equals 0. I give you a warning. I'm going to be using a lot of stuff right now from classical electromagnetism, which you won't be familiar with, but I will give you the page to look at in a textbook. So please read it, because if you're doing the quantum theory of electrodynamics, you should technically know the classical theory. Otherwise, so just, take it with a grain of salt. So the electron, we'll call this an electron. receives a kick at t equals 0. Okay. So what's the current? What's the current of this guy moving around? So at x equals 0, we can write down a current. Or a current density. That's really the right way to say it. Where J mu of x equals 1, 0, the 4 vector mu, even though it's just a 1, dotted with e times a delta function at that point. Makes sense that your current is only the charge in this situation at rest. So if I want to calculate this current from point A to point B, I can simply take the integral dt, right, moving that through in time, where I have the same 4 vector dotted with e delta 4 x minus y of t, by something like that. So now I moved it to some other, I'm shifting it. Okay, where y mu of t equals t 0. Where's a good discussion of this idea? Well, no, let me find the page for you. Yeah, I would certainly, for the classical discussion, is that look at page 703 of Jackson. Okay, Jackson Electrodynamics goes through this argument in more depth, 703. This book is hated by everyone, but it's the only good electrodynamics textbook. There's really nothing else that has everything. Although the problems in here make people cry. I'm just warning. Luckily, we didn't use this as my textbook. We used probably a worse textbook, actually, in my class, in my opinion. Just Landau. Anyways. Okay, so I've set up the problem. Let's work things out. I really haven't motivated anything yet. Let me think, how do I want to set this up? I'm thinking about this. Let me see. Let me think for a second. Just let me really think about this for 1 second. Let me see where I want to go. Okay. Okay, good. Okay. So now we've written down an expression for the current. And now we know that the current will fall off at infinity as time increases. Eventually the current will fall off. It always vanishes at infinity. And so let's write down for any test function. Erase this up top. Let's consider a test function with some current. A test function acting that tells me the trajectory of the particle. So I have some d4x. Okay, let's do that. F of x, d mu, j mu of x. This is just the current, some constant. And now if I input my y, right, I'm going to get integral d4x. So evolving this at some time, right, I get f of x e. Okay. Integral now d tau, because we're going to parameterize it by some proper time tau, right? Y mu of tau, d tau, d mu, delta 4. Just telling me how it's evolving through that time. X minus y tau. Okay. So this is giving me some current for some test function as the thing moves. Of course, we know this guy should be what? 0, right? Because d mu j mu is 0. I'm just writing, and we know that as you go to infinity, this integral is going to vanish anyway, just because current vanishes, the current vanishes at infinity. Okay, so I'm just writing this expression out to motivate something. So if you compute this integral, what do you get? Let me just think. You're going to get a minus e. I'm just going to pull it outside and do the integral. Integral d tau, d tau. Not do the full thing. Only do one piece. F of y of tau. Yes. And this is trivial. This is just minus c f of y of tau, evaluated from minus infinity to infinity. And of course, we know this has to vanish. That's a given. Okay. And I'll leave it there. We'll work with this next time, and we'll finish the classical story. And hopefully, if you read Griffiths, you'll get some more insight. But all I've done is I've said, but you don't know where we're going with this yet. Trust me, we're going in the right direction. Okay, so what have we done today? And what are we going to do next time? Let's review. So next time we're going to do we're going to do the quantum computation. First of all, we're going to finish the classical. Can I erase this board? Let me just remind myself where we ended. Okay, very good. I'll probably just do the whole classical thing over, but much faster. Okay, so we did the classical calculation. We're going to finish the classical calculation. Johnson, since you're here, I know what I want you to cover next week. Can I tell you?
Yeah, sure.
Cover soft Bremsstrahlung. Bremsstrahlung. Guess the spelling, I don't know. Okay, cover the whole calculation for that. The classical one. And you can use Jackson. Can someone tell Johnson what page I referenced? I forget.
703.
703. Perfect. We're going to do the quantum computation of this. Johnson will take care of the classical next time as well. Although I want to work this out more carefully. I want to make sure it works. Okay, and then we're going to do the electron vertex function. And we're going to finish by beginning the magnetic moment of the electron, magnetic moment electron. So Schwinger's calculation. Okay. We all good? Okay. So please read those papers by Schwinger and Weinberg. Look at all the reading. And I think after we do that, we'll begin renormalization. We'll move away from QED. We'll do proper renormalization, and we'll talk about beta functions and so on. Okay, does anyone have any questions?
I was gonna ask like an unrelated question
Yeah, of course.
about cosmology. So I was reading an article yesterday about the Hubble constant and it got me very confused. So
That's good.
so it said that the Hubble constant decreases over time, that it was larger in the past, right?
Yes.
But also the expansion rate of the universe increases over time.
Yes.
Yeah, so then how is it that, like, the reason that when you like look at distant galaxies, the reason that like they seem to be moving faster is because the Hubble constant was higher in the past, right?
Yes.
That's what I read. Um those seem kind of conflicting, that like the expansion rate increases over time, but the objects were moving faster in the past. How does that work?
Yes. Very good. First of all, in any equation in cosmology, where did you read this? Just so I have context.
It was like a Forbes article.
Okay, that's why. No, because it's important. You will always see this. Therefore, as this gets smaller, your expansion rate gets bigger. So you always see the inverse of the Hubble constant in any equation of cosmology.
Right.
So that should answer your question, because they are contradictory. How is the Hubble constant getting smaller and the expansion rate is increasing? Doesn't make sense. Should be the opposite.
So the
Yeah, go ahead. Go ahead.
So the inverse of the Hubble constant decreases over time?
No. If the Hubble constant decreases over time, the inverse is going up.
Oh, right.
Yeah, so
Okay,
that's
yeah.
why the expansion, okay? So
Right.
that's why it works. Okay, so it's a
Okay.
stupid thing that's how things are formulated. The second thing to consider is in some cosmological theories, there's also this guy floating around, cosmological constant. And so if you have it, see, it's complex, it's a little, these things, that's why it's hard, because oftentimes these things are not written by physicists, which is fine, it's okay, but they miss subtleties, right? So oftentimes in theories, you'll have a cosmological constant. I should stop recording. I don't want people to